Yeah, good evening. So let's wait for one more minute. Okay.
Okay, sir.
Yeah, good evening. So I think the last class we started. Hello.
Sir.
Yeah. Can you hear me?
Yes, sir.
Yeah. Okay. So last class we completed about the carbohydrates, and carbohydrates we started at glucose, and in which we gave some reactions for the evidence of glucose structure. Right. The first one is by the way of checking out the molecular formula of glucose just by combust that glucose product. Then from that we can able to find out how much amount of carbon, how much amount of hydrogen, how much amount of oxygen is there. There we can find out empirical formula. So empirical formula, from that empirical formula we can able to find out that molecular formula. Okay, that's the first one. And second one, what we discussed, the same glucose will be taken. That will be reacted in presence of a HI with the heat over a prolonged time. What it will give? What it gave actually? It gave N-hexane as a long chain compound. So which means that it proves that all the carbons are connected in a straight chain. Okay, so this was the second finding. And what about the third one? The same glucose will be taken and will be reacting with NH2OH, hydroxyl amine. If I'm reacting with this, I will get formed the oxime as a product. Okay. At the same time, if it is the same glucose which will be reacting with the HCN, it forms what? Cyanohydrin. All these tests on these two tests are confirms the presence of C double bond O group presence. Okay, the presence of carbonyl group can be indicated by the reaction of hydroxylamine as well as with HCN. Okay, and then the same glucose which will be reacting with another thing, that is bromine as well as water. So it will be acting as a mild oxidizing agent. It forms a gluconic acid. Gluconic acid. Yeah. Gluconic acid it forms. Suppose if it is react with the same glucose which will be reacting with a strong oxidizing agent like a concentrated HNO3, then it forms
Saccharic acid.
glucaric acid. Very good. So glucaric acid. Okay, glucaric acid. Yeah. These are all the confirms the presence of the primary alcohol. Okay. After that, we gave another evidence, that was which consists of a 5 OH group, and all the OH groups are attached in different carbon. That can be checked with the help of anhydride. When glucose reacting with anhydride, so in presence of a pyridine, because one of the product formed here is, so here pentaester will be formed. Pentaester will be getting formed. That pentaester confirms that 5 OH groups are there, because when acid anhydride, which is reacting with that alcohol containing groups like OH, it forms ester. If pentaester is getting formed, means 5 OH groups are there, that confirms. And all the 5 OH groups are attached in a different carbon also, we confirm. Because why? Because in a single carbon, if 2 OH groups are attached, then it is a highly unstable compound. It can left over as water molecule and form carbonyl compound. So this will not be taking place in glucose, because glucose is a stable compound. That is what we confirm, that 5 OH groups are attached with the different carbon atoms. So, okay, these are all the findings we find out. And also there will be a formation of some acid is there. So to neutralize this acid only, we are adding this as a base. So pyridine will act as a mild base to neutralize the acid formed in the reaction. These are all the confirmations we did to find out the structure of glucose. From that, we got a structure like this, that is C double bond OH, one aldehyde group is there, and C OH, and here H is there, here one H, here OH is there. After that, remaining all same, the C OH, here H, C OH, here H, here CH2OH. Okay, these are all the findings. Based on that, we gave the structure like this. Okay. Yeah, this is a structure of glucose, but the structure of glucose is highly stable. Okay, that's what the 5 OH groups are in different carbons. And one more thing, the stereochemistry of this one can be studied by the Fischer. The Fischer studied that stereochemistry of this glucose. Stereochemistry of glucose studied and he gave the confirmations also, studied by Fischer. So Fischer studied the structure and studied about that stereochemistry, and he also gave some structure. What is that? Same structure he provide. That is CHO, because we know that Fischer projection will be consist of a backbone of carbon. Okay, so OH here and here H. Here H, here OH, and also here OH, here H, here OH, here H, here also OH, here also H, and here CH2OH, right? So which consists of, these are all the carbons. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. I think so. I excessively put one carbon. Yeah, here CH2OH, right? CH2OH, CH2OH, yes. So totally 6 carbons are there. Okay. And then how many isomers are possible for this kind of things? Because it entirely based on the how many number of chiral carbons are there. What are all the chiral carbon? I think so last class we studied about that chiral carbon. Yes. How many chiral carbons are here?
4.
4 chiral carbons. Why only 4 chiral carbons? Why cannot this CHO will not be a chiral molecule? Chiral
Double
carbon?
bond is there, sir.
Because that has sp2 hybridized. Okay, sp2. Why this CH2 group will not be in chiral?
2 hydrogens are there.
Two same groups are there. Okay, so asymmetry is not there. So here, so 2 similar groups are there. That's what will be considered as chiral molecules. So only 4 chiral molecules are there. So according to that, 2 power 4. So 2 power 4 is the set 16. So there will be a 16 possible configurations.
So I have a doubt in the structure, sir.
Yes.
So why is one OH on the left alone, sir?
That's a stereochemistry. So that is the structure of glucose. So even the arrangement of atom in a 3-dimension will be looking like this. Okay. Because
sir.
that carbon will rotate the Fischer. If you look at, because that is not, stereochemistry is not discussed in your topic, but just for the information only I am giving. So actually the Fischer studied. So in that second carbon, that stereochemistry will changes. Suppose if you pass a plane polarized light to the particular carbon, that may rotate to the different direction also. Okay. So based on that only, he may given that kind of structure like this. The OH group will be pressed third carbon, the OH will be present in the left side. Okay.
Okay, sir.
He may come to that conclusion because of that rotation.
Understood, sir.
Out of which 16 possible configurations, only one is. So one of them is yes plus D glucose. So we are studying about only plus D glucose. Okay. So we have how many possibilities? There are 16 possible configurations are available. Out of which we are going to concentrate only one. Okay. So that is given your syllabus. And when you go to higher studies, so through that chemistry, so you will get our biochemistry like that. So you may study about all these topics very detailed. Say for example, we know that, say for example, here I am giving you some examples like this, CHOH, and here H, and here CH2OH, and here also, what is that, CHO. Yeah, what is the name of this compound? Can anybody know? I already told you in last class, this is the, what is that?
Glyceraldehyde.
Simplest carbohydrate or smallest carbohydrate. Yeah, glyceraldehyde, very good. Glyceraldehyde. Okay, glyceraldehyde consists of why here it will be considered whether it's a D-glyceraldehyde or L-glyceraldehyde. How will you identify D and L?
Position of OH group.
Right, then it's D.
From from bottom to the top carbon, bottom to the second carbon. If OH group is on right side, then it will be coming under the category of D. Am I right? There is D-glyceraldehyde. This is D-glyceraldehyde. If OH group which is present in left side, then it is called L-glyceraldehyde. Okay, CH2OH. This is called L-glyceraldehyde. Why? Because the OH group is in left side. So from the bottom carbon to second carbon, so that in that the position of OH group is in right side or left side. Based on that, it will vary. Okay, this is L-glyceraldehyde. This is L-glyceraldehyde. Is it clear? So let's confirm. There is this is also coming under the polyhydroxy aldehydes. Am I right? Because this is also coming under carbohydrate category. What is the definition for carbohydrate? New modern definition for carbohydrate is what? Anybody? If the compound wants to be coming under the category of carbohydrate, it should be optically active.
Optically active polyhydroxy.
Yeah, optically active polyhydroxy. Very good. Polyhydroxy aldehydes or which can produce some kind of same kind of units during hydrolysis. Okay. So this is what the structure of glucose and stereochemistry also like this. And very important thing, and some of the studies will not confirm the glucose, it's not a straight chain molecule. So there will be a failures of straight chain structure of glucose. Straight chain structure of glucose. Some of the studies, they confirms glucose is not a straight chain compound. Okay, so what are all that? So let's check one by one. The first thing is glucose does not show some test to 2,4 DNP. 2,4 DNP test will not be taken place here. In glucose, it is not taking place. And Schiff's base. Glucose is not getting react with Schiff base. Glucose is not getting react with the NaHSO3, sodium hydrogen sulfide. Okay, so all these reaction will confirm glucose is not a straight chain molecule. How? And one more test also confirm the same. That is a pentaacetate of glucose. Pentaacetate of glucose does not reacts with hydroxylamine NH2OH, okay, to form oxime. Okay, so these are all the simple tests which are not confirms the structure of glucose is sorry. If these tests, that means the glucose will not undergoing these kind of tests, will not show any positive result for these tests, which confirms the presence of, which confirms the absence of a straight chain molecule. Okay, glucose is not a straight chain molecule that can be confirmed by these tests. So what do you mean by 2,4 DNP test? We heard about that. I think so. We completed in that alate ketone chapter also. I think so. So 2,4 DNP is nothing but 2,4 dinitrophenylhydrazine. Phenylhydrazine. Yes, what do you mean by hydrazine? What is the structure of hydrazine? NH2, NH2. That is the structure of a hydrazine. Okay, in which one of a hydrogen can be replaced by the phenyl group. That is what may be called as a phenylhydrazine. In that phenyl group, in the second position will be occupied by NO2 and fourth position will be occupied by NO2. This is what it is called 2,4 DNP. It is a kind of ammonia derivative. Whenever the ammonia derivative which is reacting with any aldehydes or ketones, when ammonia derivative is reacting with any aldehydes or ketone, that shows a positive test. It forms its respective phenylhydrazone. Check what's the reaction. So suppose when aldehyde is there, or C double bond OH is there, if it is reacting with H2N, NH, I'm just writing phenylhydrazine molecule. Here N go to second position and fourth position also N go to. So what kind of product it can give? So you just remove this water molecule. So then straight away you can write the product. That is RCH, and also double bond is there. This double bond I can written here. And then straight away you can attach with the nitrogen, NH, and finally we have the phenyl nitro group. That is 2,4 dinitrophenyl group. Okay, this is what this confirmation test should be given by 2,4 DNP. If an aldehyde is there in a molecule, if it is reacting with the 2,4 DNP, that shows positive test of 2,4 dinitrophenylhydrazone. Either it may form a red color or orange color or yellow color. Yellow color solution should be turned up. Okay, so when these aldehydes are reacting with 2,4 DNP, it should form either red or orange or yellow color solution. But here when glucose reacting with 2,4 DNP, glucose reacting with 2,4 DNP, it does not shows any result. Okay, no reaction, which means that what? Glucose containing aldehyde group is not in free state, which confirms in glucose the aldehyde group will not be in the form of CH2 as it is. because somewhat it is in different form. That confirms the that confirmed by 2,4 DNP test. Is that clear? So when 2,4 DNP, if it is reacting with aldehyde, it should form these kind of any colors, okay, either red or orange or yellow color solution to be turned. Okay, but glucose also, because we predicted the structure of glucose here as aldehyde, am I right? Here he gave the structure as CHO. Glucose has CHO structure, but even though it does not show any kind of 2,4 DNP test. Why? Because the glucose which will not be in the free state, which confirms the aldehyde group will not be in free state. Okay, is that clear, Kana? Is that clear or not?
Yes, sir.
Yes, sir.
Fine. Shift base. When the glucose which is reacting with the shift base, so there should be a red color PPT should be there. Red PPT should be there. Okay, but here it forms a colorless solution. But when glucose reacting with shift base, it doesn't form any red color PPT. It forms colorless solution. Colorless solution, which means that the glucose it's not getting react to form, because the glucose is not reacting with the shift base, because the shift base, if then any aldehyde group is there, can react, but here glucose does not contain any free aldehyde. So the above two tests will confirm the above two tests confirms the CHO group is not in free state. It's not in free state. It will be available in some other form. Okay. And one more thing, NaHSO3 also. NaOHSO3, which confirms the presence of carbonyl compound. C double bond O group is there. That can be confirmed by NaHSO3 test. Okay. If it shows positive result, so it forms there will be a presence of C double bond O group also. Okay. But here also that kind of things also absent or not absent. It will be available in different form. Okay. So what kind of form it is available? So that can be given here. So here, so the glucose may be in the form of cyclic structure. So the straight chain structure explanation will be failure, right? Some of the tests will not give the positive test when it is reacting with the glucose, which confirms the glucose will not be in straight chain. So it may be in the form of cyclic structure. So cyclic structure means what? Say for example, before getting to the cyclic structure, we must understand this concept. What is that? So when aldehyde reacting with an alcohol, say for example, CHO is there, and if it is reacting with an ROH, then what kind of product I can get it from here? So from where the reaction is getting initiated? The reaction is getting initiated from the lone pair of alcohol. And then this lone pair can go and attack. Where it will go and attack the lone pair? The lone pair of electron, where it will go and approach?
Carbon.
It will approach carbon. Why, Kana?
Because oxygen will be slightly negative and carbon.
Yeah, oxygen has slightly negative. That's what it's highly electronegative element. So the carbon may have some positive charge. Okay. So if carbon undergoing attack, but already carbon in 4 bonds, but carbon will not be existing in 5 bonds, so that this electron can be transferred to that oxygen. Then what will happen? So R, C, here O minus, here O, R, and here H is there, and here also an H is there. Am I right? And here there will be a positive charge. Why? Because the oxygen donate electron. That's what It loses electron, so it has positive charge. Then what will happen? Oxygen is highly electronegative. Then it can pluck out the electron from the hydrogen. The hydrogen will donate electron to the oxygen because oxygen becoming highly electronegative. Because if oxygen is highly electronegative, already it is electron deficient. Okay, so if positive charge is present means still more and more electrons are required. That's what it can quickly pulls the electron from that hydrogen and it can cleave that hydrogen as H plus. And this H plus will go and approach where? It will go and approach to that oxygen. Then R, C, H, OH, and here OR. Okay, this is called hemiacetal. Hemiacetal. Is that clear? There will be a formation of hemiacetal will be there. So what is that? One side we have R group, one side we have OR group, OR dash. One side we have OH group, one side we have hydrogen. Okay. If the molecule is like this, it forms a hemiacetal form. So here the aldehyde can react with the alcohol. So where the aldehydes and alcohols are there in glucose? Let's write the structure of glucose. So here again C double bond OH. Why I'm writing? Because why I'm not pasting? Because you will get understand then only. So where we have to write, where we have an exception, so you have to concentrate all those things. Here H, because in this chapter you must practice it well, or otherwise you can't write the structure. Okay, so you'll get forget many things because entirely the carbohydrate is only a toughest question. Remaining all are easy. Okay. And here we have a aldehyde group is there. Okay. And here we have alcohol because it's a polyhydric aldehydes are there. That is glucose. Am I right? And this alcohol may contain the lone pair. Okay. That may go and approach this carbon to make it in the form of hemiacetal. Okay. Now, how it will be there? So if O minus is there, same thing, same mechanism. So whatever we see in that above, the same mechanism will happen. If OH group is there, the OH group will go and approach here this carbon. The carbon will get 5 bonds, then it will shift over the electron. Then what will happen, Tana? See here O minus, here H is there. Am I right? And then remaining are same. COH, H, then CH, here OH, and then COH, H, and then C, here H. Here there is no OH. Why? Because that is going to approach this. Okay. And this minus charge, and because of that loss of this lone pair, this carbon will get positive charge. And this positive negative will form a bond. Okay. Now the oxygen I can write it here itself. Okay. I can write the oxygen in between. Is that clear? Is it understandable or not? And here CH2OH. Is it understandable or not?
Understandable, sir.
Yes, sir.
Understandable. But you have one question. I'll tell you what kind of question you have it. So because why that only this OH group should attack? Why can't this lone pair can attack? Why can't this lone pair can attack? Because this here also the oxygen is there. Here also the oxygen is there. By what? Why it can't attack? Why? Do you know any reason about that? Do you have any reasons?
So could you repeat the question?
Yeah. Because why specifically I taken this oxygen? Why can't this one, this one, this one? Because the attack can be done by the from bottom to second carbon. Why? Because then only suppose if this carbon, you just assume it, yeah. If this carbon, this oxygen will go and approach, the ring size will be very small. If the ring size will be very smaller, then the structure will also be very less stable. That's what it can try to form the big ring-like structure. Okay, that is what if this OH containing that lone pairs can go and attack to form a six-membered ring. How it form a six-membered ring? Because this is a carbon number 1, 2, 3, 4, 5, and sixth one is oxygen. Am I right? There will be 6 atoms are there. So 5 carbon atoms on 1 oxygen atom. That is what they form, six-membered ring. Six-membered ring. So that is what it is highly stable. For the stability only, it forms six-membered ring. That is what these lone pairs cannot go and attack. These lone pair cannot go and attack. Okay, like that. Is that clear? So somewhat it forms a hemiacetal structure. Is it clear or not? Well, this is very, very important. Is it clear or not? If you said clear, I will move on to next. Otherwise, I'll repeat.
Yes, sir.
Very, very
I have a
simple.
doubt.
Just it can form hemiacetal. Nothing but it forms hemiacetal. Alcohol and aldehyde reacting to form hemiacetal. That will be given in the top. Okay. In the aldehyde also, the glucose also consists of aldehyde as well as alcoholic group. So the alcoholic group which is present in the glucose, which is reacting with aldehyde group, then it forms hemiacetal ring. Forms a hemiacetal like structure. That's what they become more stable. So now the glucose.
I have a doubt, sir.
Yes.
So in the cyclic structure you've drawn, the first carbon should have an OH, no, sir? If you, according to this.
It's OH. Yeah. Stick off. It's OH one. Yeah.
Okay, sir.
Yeah, next. So the six-membered ring become a highly stable. That is what it forms, six-membered ring-like structure. So either can attack by only this way. Either it can attack because we know that this aldehyde which consists of sp2 hybridized carbon. sp2 means what will be the structure? What is the expected structure? sp2. What is the expected structure for sp2? If the hybridization is sp2, what will be the structure? So you studied about sp, it is a linear. sp2, it is
Be cyclic, sir.
cyclic or trigonal. sp3 means tetrahedral. You studied in P block, no? Definitely you must study in P block. Okay. sp3 it's a tetrahedral. Then sp3d, what is that? Trigonal bipyramidal structure. sp3d2, what is that? Octahedral. Yeah. sp3d3, what is that? Pentagonal bipyramidal. Okay. So you studied about the structure of group 17 elements, group 18 elements. You studied now. So where this is available. Yeah. So then here C, OH, and here also H, and here C, OH, and here also H, and here CH2, OH. This is the structure of glucose. Suppose this oxygen will attack from this side. Why? Because it's a sp2 hybridized. sp2 means a trigonal. Trigonal means it's a trigonal planar. It's a trigonal planar. If it is a planar, so the arrangement will be like this. The C double bond O H. It will be like this. So either this carbon will attack from this direction or this carbon will be attacked from this direction also. either from front side or it can from back side. Okay. So in 3 dimension, you should assume that in 3 dimension, because the 2D in 3 dimension, if you look at either that electron can approach from the front side of the carbon or the back side. Okay. So if it approaches the front side of the carbon, I'll get some structure. What is that? I'll get this structure, same structure. What is that? So here CHOH. Again COH. Here H. Again third carbon, it is different. So here H. Here it is OH. What about the fourth carbon? COH and H. And fifth carbon, only carbon is there, only hydrogen is there, and sixth carbon CH2OH is there. Am I right? And this carbon, only this side, we have a ring. Okay. You assume this, the ring will be formed, but the electron will be approached from this direction. Okay. Then only the OH will be on right side of that group, or otherwise it may be present like this. Yeah, now we can have. If suppose the attack from the green color like this, the green color attack, okay, so what it will be? So it will be forming a structure like this. What kind of structure can it can form a structure like this? See, here H, here OH, and here C, OH, H, and here also C, H, OH. And here also C, OH, H. Here also C. I can write the ring like this. And here CH2, OH. And here one hydrogen. Is that clear? So in this case, here we are going to classify these glucose into other category. We know that it is a D glucose. Am I right? This is a plus D glucose. How I can say it's a plus D glucose? Because the OH group which are present in right side in both the case. That is what is also plus D glucose. This is also plus D glucose. Is that clear? So for the naming only, we are using that D and L also. Because if OH group which is present in the left side, then it is called L glucose. Where which carbon? From bottom to second carbon. From bottom to second carbon, if OH group are present left side, then it's called L glucose. But here in both the case it is, because in this case here it is a D glucose only, na? D glucose. Okay. And plus and minus, what it says plus and minus. What's the meaning of plus and minus?
Dextrorotatory or
yeah, it is a optical the optical activity given by plus and minus, right? If it is a dextrorotatory, plane polarized light will be passed to that, which will rotate the plane polarized light towards to clockwise direction. Then it is called dextrorotatory. Okay, the glucose, D glucose, plus D glucose, it's a dextrorotatory. That is what is called as plus. Okay, the D will not given the information about the optical activity. D and L, capital D and L will confirm only naming whether the OH group which is present bottom to the second carbon. Okay, that carbon which consists of OH group on right side, then it is called D. If it is in left side, then it's called L. Okay. And here we are going to classify this because both the structures are not same. Am I right? Why? Because here the OH group is in first carbon. In first carbon, the OH group is in left side, and one case OH group is in right side. You just remember it. If the OH group which is present inside the ring, you just it's a trick. Okay. So if the OH group present right side, or you consider that within the ring structure, the OH group is there, then it is called as alpha D glucose. What is that? Alpha. The alpha and beta will be given like this. And if OH group is on left side in the first carbon, then it is called beta D glucose. Okay, this is called beta and this is called alpha. Which carbon? First carbon. In first position, if OH group is on right side, then it is called alpha. If first position OH group is on left side, then it's called beta. So it's called alpha D glucose and beta D glucose. Is that clear, Kana? Is that clear or not?
Clear, sir.
Fine, good. And these two carbons are anomeric carbon. First carbon, the first carbon, this carbon and this carbon are commonly called as, what is that? Anomers. Anomers. What do you mean by anomers? So the only change is, if you flip the carbon, one, the position will change. The beta will become alpha, alpha will become beta. That's it. That's what is called anomeric carbons. Okay, that's called anomer. Okay. And we know that alpha D glucose structure, beta D glucose structure, we know the entire structure of alpha D and beta D glucose now. So we know that first thing is, we have to write that, what is that, Hawath projection from this one. Okay, for writing Hawath projection, just it will be considered 6-membered ring, na? 6-membered ring. One position will be combined, that means occupied by oxygen. Remaining all are carbon. Okay, this is what we have to write. This is called the pyranose structure. Pyranose. It's a pyron structure. The pyron will consist of double bond also, but just for understanding, it is enough. So pyranose structure. Pyranose means 6-membered ring which consists of oxygen. That is called the pyranose structure. Okay, and here glucose will also having cyclic structure. And here one more thing also, because that another stage will also be there, which will not be given in book also. Okay. Here, totally how many carbon atoms? 6 carbon atoms. Am I right? But if you consider in this molecule, how many carbon atoms are there in this molecule? It's a cyclobutane. Okay. How many carbon atoms are there? 1, 2, 3, 4. Am I right? Hello. Can you hear me?
Yes, sir.
Yeah. How many carbon atoms are there? One carbon number 1, 2, 3, 4.
4.
But this structure will also having some queries. What is that? Here we consider this 1 carbon, 2 carbon, 3 carbon does not contain 9 carbon atoms. Okay. Okay. This structure will also coming under what is that? Some risk. So because the structure contain only 6 carbon atoms. Okay. Yeah. Hawath projection. The Hawath projection. How to write a Hawath projection from this Fisher projection? How we can write it? Say for example, I can write now that C H here O H. So just I'm going to write the structure, that is C O H again here H, and in the third carbon we know that C here H here OH, and in the fourth carbon as usual OH H. From the fifth carbon the ring will be attached, and here the oxygen is there, that will be connected to the first carbon. Okay, and here one hydrogen is there, and here CH2OH group is there. Okay, what is the structure? Whether it is a alpha D glucose or beta D glucose?
Beta D glucose, sir.
It is beta D glucose, right? It is beta D glucose. How you find out the beta D glucose? The presence of OH group in first carbon. If it is on left side, then it is called beta. If it is on right side, it is called alpha. Or you can assume that within that ring, if OH group is there, then it is alpha, or otherwise it is beta. In the third carbon also, we have C, here H, here OH. And here also C, OH, and here also H, here C, and here it is O, will be attached like this, and here H, and here CH2OH. And this is called alpha D glucose. So we know the structure of alpha D glucose. Am I right? Alpha D glucose as well as the beta D glucose. How to write the How to convert the structure from alpha to beta? How we can convert alpha structure to beta structure? Sorry, not alpha to beta. So from what is that? Fisher projection to Howard projection. How to do that? So we know that glucose exists as six-membered ring. Six-membered ring. Okay, which means that there will be a hexagon you have to take. Okay, and here you have to keep oxygen on the top right corner. Right corner. You have to keep the oxygen in top right corner while you're writing the hexagon. Okay, so a six-member ring, which is nothing but a hexagon. Okay, hexagon. Yeah. And what is the next rule? Then we have to start numbering. Start numbering from carbon from the right side. Okay. Then bonds will be represented as bonds are represented as vertical lines. Vertical lines. Then you have to give the functional groups. Yes. So the step by step. So first of all, I have to write the six-membered ring. So out of which, what is that? Oxygen should be keep it on the top right corner. Yes. And then I written six. I drawn that. What is that? A six-membered ring. This is called a six-membered ring, which consists of one oxygen atom on the top right corner. Yes, I wrote that. Then we have to number it the carbon. Okay. Then we have to number the carbon. This is carbon number 1. This is carbon number 2. This is carbon number 3. This is carbon number 4. This is carbon number 5. Then I have to keep a carbon number 6 here. Okay. This is carbon number 6. Yeah, this is carbon number 6. Yes. Then what I have to do? So I have to give the bonds. Bonds will be given in vertical lines. 1, 2, 3, 4, again 5, 6. Then you have to give the function. Yeah. So how to convert this? How to write this structure? Do you have any idea about that?
In the glucose structure, whatever is on the left, we write on top, sir.
Okay, we have to write that. Okay, fine. So you have to keep this word write down. Write down. You just memorize this. You just make it as a tip. It's a write down. The word write down. You should memorize this. Why? Because whatever the group which is present on right side, you have to give it in bottom. Okay, you have to give it in bottom. Then how we can give the structure? For that, if I'm writing the structure here, let's write it for alpha D glucose. So here OH group is in right side. That is what I can write it in down. And in second carbon, OH group is in right side. That's what I put it in second question, down question. And here third carbon, hydrogen is in right side, so that I have to written in down. And here fourth carbon, OH group is there, that will be given in down. And then fifth carbon, no problem with that. Then sixth carbon, fifth carbon, only hydrogen is there. So hydrogen we can write down. Okay. What about that? Here fifth carbon, this one now. Yeah, that will be given on left side. So that we have to write like this. Then fifth carbon, we have O group. Am I right? So totally yes. 6-membered carbon atom. Then sixth carbon will be represented like this. How to represent the sixth carbon? Sixth carbon will be like this. CH2OH. Is that clear, Kana? And then remaining groups, we have to add left side, whatever will be there, that will be write it in top. Write down, and here, sorry, here OH, here H, and left side we have CH2OH. So what is the structure of this one? This is called alpha D glucose. This is the structure of alpha D glucose by Haworth projection. And can you convert now in that beta D glucose?
Yes, sir. Only OH position first carbon will change.
Yeah, just I'll draw, then you can tell. Then 1, 2, 3, 4, 5, 6 like this. Yes, now in first carbon, what is present right side? Hydrogen. And here OH is on top. Okay. And second carbon, OH is on bottom. And third carbon, OH is on top. Fourth carbon, again OH is on bottom. Fifth carbon, hydrogen is here, and sixth carbon, CH2OH. Is that clear? Is that clear? And remaining we have to satisfy with the hydrogen. So then we can write like this. So we can write the structure. Here hydrogen, here hydrogen, here hydrogen, like that. Okay. If it is a beta D glucose, so we have a simple trick. What is a simple trick to write the beta D glucose? Beta D glucose, all the OH groups are in alternate position. Alternate position sense, first top, then bottom, then top, then bottom, then top. Okay, so alternate position will be there in beta D glucose, but in alpha D glucose, first and second carbon atoms are having bottom. The OH group will be present in the bottom carbon. Is that clear?
Yes, sir.
Is it clear or not? Is it clear or not?
Yes, sir, it's clear.
Yeah, okay, fine. So, okay, now, which are whether alpha D glucose or beta D glucose, which is more stable among these two? Which is more stable, either alpha D glucose or beta D glucose? Actually, the more stability will be for beta D glucose. This is a stable one. Why? Why it is highly stable? Because it has two reasons. Okay, the first reason is alpha D glucose, it is highly unstable. Why? Because the OH groups are very near to that. Okay, they are very closer. They are very closer. They have repulsion. Where the repulsion, the oxygen contained lone pair repulsion will be there. That is what it is highly, somewhat when compared to that beta D glucose, alpha D glucose is less stable. And one more reason why beta D glucose is highly stable, because it can form a hydrogen bonding with this oxygen. Now you can consider here the OH group is in top now. So here OH group is in top. Now this oxygen hydrogen will form a hydrogen bonding. So that is what become highly stable. Okay, there are two reasons. So one is alpha D glucose, which is very less stable due to lone pair repulsion. And beta D glucose is highly stable due to the hydrogen bonding formation. Okay. So out of these two things, so beta D glucose is highly stable when compared to alpha D glucose. Okay. And here alpha glucose and beta D glucose. Beta D glucose. And what is that melting point of this one? This is 419 Kelvin. And here it is 423 Kelvin. That is what somewhat highly stable. Okay. Highly stable. And normally, what is that? The crystallization. Here the crystallization of concentrated solution of glucose at even 30 Kelvin, almost not 30 Kelvin, almost 30 degrees Celsius, 30 degrees Celsius, around 303 Kelvin. Okay, around 303 Kelvin, which means that almost at room temperature, almost at room temperature. But here, crystallization of hot and saturated solution at 371 Kelvin. What do you mean by saturated solution? Saturated solution. What is saturated solution?
And no more solute can be dissolved in it.
Yeah, no more solute can be dissolved after particular stage at which a particular temperature. Okay, that is what is that? What is that? What I said? The saturated solution. Okay, so here almost alpha D glucose 419 Kelvin and here 423 Kelvin, and the crystallization of concentrated solution of glucose will be taking place at room temperature itself. But here it required a high temperature. Almost it required near to the boiling point of water temperature, almost 100 degrees Celsius. Okay, is that clear, Kana? Is that clear?
Yes, sir.
Yeah. And just a minute. And in this case, we found out the structure alpha D glucose and beta D glucose. You found out how many number of chiral carbons are here in this case, or in this case, how many number of chiral carbons are there?
6, sir.
No, 5 only, no? How will be 6? This won't be acting as a chiral carbon because both the sides we have 2 hydrogen atoms now. So initially, when glucose structure was proposed as straight chain molecule, straight chain structure, in that case we have only 4 chiral carbons. But here sp2 hybridized first carbon, that is aldehyde group, can be converted into hemiacetal form. Then it becomes 5 chiral carbon containing. Okay. And here generally hemiacetals are highly unstable. Hemiacetal forms are highly unstable. Here hemiacetal forms are unstable. Then how glucose is stable, sir? Hemiacetal forms are highly unstable, but in 5 or 6 membered ring, they are extremely stable. Okay, extremely stable when it is present in 5-membered or 6-membered ring. So these are all the reaction which will be the stability can be checked by that as an experiment. Okay, that can be done by experiment. Okay, is that clear, Kana? Very simple. So we have to write the pyranose structure, and this is what they may be called as glucopyranose. What are that? These are all called as, otherwise called as a glucopyranose. Glucopyranose. This is called what is that? Alpha D glucopyranose. What about this one? This is alpha D glucopyranose. Because it resembles the structure of pyranose. That's all. And
So should we add the plus sign here, sir, when naming?
Yeah, we can write also plus sign because both are plus D glucose only. Okay, you can write the plus sign also. That's not a problem. Okay. Yeah. And next one is what? What about the next one? What will be the
Fructose,
glucose? Yeah. In that glucose, what will be the next part? Have you all studied about this? The next important thing is, what is that? Mutar rotation. We talk about the mutar rotation. mutarotation. What does mean by mutarotation? Mutarotation is nothing but the rotation of pure alpha D glucose and beta D glucose changes over time to reach an equilibrium value, and this phenomenon is called, what is that? Mutarotation. So what is that mutarotation? So alpha D glucose and beta D glucose. Yes, we are going to take a pure alpha D glucose and beta D glucose and changes over time to reach an equilibrium value, because these all consist of anomeric carbon. This consists of anomeric carbon. So alpha form can become a beta form. Beta form can become an alpha form. Okay, the percentage may vary. So both cannot attain equilibrium as much easier. That is what they have a mutarotation. That means it will take more time to reach an equilibrium, because that is what is called a mutarotation. That clear? So alpha D glucose, just I'm going to take a alpha D glucose in a beaker. So you consider this is a alpha D glucose. Alpha D glucose. Just I'm taking alpha D glucose because all are in what is that? Positive. Positive in the sense what? Positive means they are dextrorotated. Okay. When the plane polarized light, where do you get plane polarized? What is mean by plane polarized light? What is plane polarized light? Anybody?
Light pass through a glass prism, sir.
Light pass through
Glass prism.
Then what the light become actually? Why it is called as a you said it is right, but what is the difference between that initial light and after passing into the prism? What's the difference between the light? Say for example, here I am having a light source. Here I am having some light source. And what is the light? Light can expose in all the direction. Okay. Lights can expose in all the direction. And then if we pass a light to this, what will happen? Nothing will happen. Actually, so the light can be get passed into the filter. The filter may be a prism. Okay, the filter. So which converts the light into unidirectional light. Any direction, either this direction or this direction or this direction. It can act as a filter. Okay, so this will be this can be the prism will act as a filter which can filter all the direction lights. So it can allow only one direction. So unidirectional light, that is called PPL. That is called the PPL, plane polarized light. And when the plane polarized light which is passed to the alpha D glucose, what will happen then? We know that it is alpha D glucose, it's a positive one, which means that which can rotate the plane polarized light towards to clockwise direction only. Is that clear? Which will rotate the plane polarized light towards to clockwise direction. Is that clear or not? When
Yes,
the
sir.
light can be rotates like this in clockwise direction, this is called dextrorotatory. Okay, so it will rotate around 112 degree. Okay, so it can rotate angle up to 112 degree, 112 degree. Okay, suppose the same plane polarized light will be taken here, and that light will be passed to the pure compound like what is that? Beta D glucose. So initially we have taken alpha D glucose and just Now we are going to take about the beta D glucose. What will happen? So it will also rotate the light towards to clockwise, but the angle will be only 18. What about that? 18 degree. This is also plus. This is also plus only. This is also dextro rotated. Because we know that D glucose. So beta D glucose, alpha D glucose, both are plus only. So it can rotate about 112 degree, and here it is only 18 degree. Yes, now because we said that is the alpha and beta form are interconvertible form. Yes, now suppose if I'm taking a alpha form here, so if I'm taking a alpha form, alpha D glucose, just I'm taking, and this alpha D glucose can get converted into beta D glucose. Okay, and beta D glucose can be converted into alpha D glucose. That is what it cannot involve in equilibrium much easier, because the conversion is continuously done. Okay, that's what it may be. Some 80% will be here and 20% will be here. So 80% alpha D glucose may be there and 20% beta D glucose is there. Okay, so if you solve this, you'll get what is that? The angle of rotation will changes. Why, Kana? Why angle of rotation will changes? Because the alpha form will have 112 degree, but beta form will have only 18 degree. Okay, but if you have this kind of composition, based on that composition, okay, it may vary. That will rotate around 57 degree. It's not Celsius, 57 degree angle. Okay, so the mixture, that means at which an equilibrium which rotates 57 degree. Okay, this is called Muta rotation. What is that Muta rotation? Because it will take more time to attain equilibrium. So the rotation of pure alpha D glucose and pure beta D glucose will be taken, and which can be changes over time to reach an equilibrium value. Equilibrium value, which it will change more time. It changes over by time. That process, that phenomenon, that is called Muta rotation. Okay, this is involving in Muta rotation. So important concept. So just you know that. Okay. And very important thing is here Muta rotation. And another important thing is whether alpha D glucose and beta D glucose, whether it is a reducing sugar or non-reducing sugar. Whether it is a reducing or non-reducing sugar. Both alpha D glucose and beta D glucose. Whether it is a reducing or non-reducing. How can we check whether it is a reducing or non-reducing? How can we check that whether it is a reducing or non-reducing? Reducing or non-reducing, it's a simple concept. So reducing, in the sense, we have to know some reagents like what are all the reagents, say, for example,
Tolerance reagents, sir.
tolerance reagent, very good. Tolerance reagent can reduce the tolerance reagent, or what is that? Another reagent is
Fellings reagent.
Fellings, very good. Okay, Fellings reagents. Any other reagents are there? Tolerance, Fellings. Apart from that, tolerance and Fellings, we can check the reducing capacity of sugars. Tolerance, Fellings. Then any other reagents are there? Any other reagents? No?
BR2 water.
Monish test.
Monish test, no.
So in presence of BR2 water, sir.
BR2 water. Okay, that's also a reducing agent, but it will not be used for reducing this aldehydes. Okay, because BR2 as well as what do you say? BR2 water. Whether it is a reducing agent. Actually, it's not a reducing agent. It's oxidizing agent. So it's a mild oxidizing agent that converts aldehyde group into carboxylic acid. Okay.
Okay.
Yeah. And next one is, yeah, it can reduce the tolerance as well as fillings. Then Benedict reagent. Okay. So if it reduces all these things, if glucose reduces all these things, which will be considered as reducing sugar, or otherwise it will be considered as non-reducing sugar. Let's write one structure. What is that? Either alpha D glucose or beta D glucose structure. So how can we write the structure of Havok projection? So here we have to write like this, and 6-membered ring I had to put. Then I had to given the bonds in vertical lines, and here if it is a OH group is there, and here OH group is here, and here OH group, and here OH group, and CH2OH. What is that? Either it's alpha D glucose or beta D glucose. Whether it is alpha D or beta D glucose.
This is alpha.
I said alternate positions are
Beta D glucose.
alternate positions are beta. Right? So it is beta D glucose. It is beta D glucose. Yes. Whether it has any hemiacetal form, let's check the hemiacetal form. Hemiacetal form is there. If the glucose, if the molecule if the molecule or a compound have hemiacetal form, then which will be acting as a reducing sugar. This is a simple way to find out whether the given sugar is reducing or not. Now we should know what is hemiacetal form. We already talked about that today itself. What is a hemiacetal form? When an aldehyde reacting with an alcoholic group, what it will form, Kana? So here the lone pair can go and attack and can keep the bond. Then what will happen? RCO minus, here 1H, here OH, and here R dash. Along with that, here positive charge. Then oxygen will try to pull the electron from hydrogen, and this will leave as H plus, and that will go and attach to the negative charged oxygen. Then R, C, H, and here we can write like this also. Here C, here R, OH, here what is that? OR and H. If the group are there, so if one carbon is attached with, you must remember these things. If one carbon attached with OH group, OR group, or hydrogen. Okay, if these three things are there, then it is called, if single carbon attached with all these groups, then it is called hemiacetal form. Okay, so whether let's check about all the carbon positions. How to check the carbon position? We have 6-membered ring now. So here it is a 1 carbon, 2 carbon, 3rd carbon, 4th one, 5th one, and 6th one. Now, can you check where we can check? First carbon we can check whether this carbon has hemiacetal form. Hemiacetal form means what? If carbon attached with one OH group, one OR group, one hydrogen. Whether the carbon 1 has hemiacetal form. Here you consider this carbon attached with the OH group. Yes, it has OH group. And it has attached with the hydrogen. Yes, it has a hydrogen group. And here it is attached with the O, and that will be attached with the carbon. This is called R. This is R. So it is, the entire group is called OR. Is that clear? So the OR, oxygen which is attached with the carbon. Carbon will be considered as R group. Okay. and OR group will also be there, and here directly attached with one more carbon, that is also OR. So which will be available? Chemiacetal form is available here. That is what? Beta D glucose is a reducing sugar. Is that clear, Kana? Beta D glucose, it's a reducing sugar. Very, very important one. Beta D glucose is a reducing sugar. How we can check? We can check with the help of what? We can check with the help of chemiacetal form. Is that clear, Kana?
Yes, sir, it's clear.
Yeah, fine. And then next one is a fructose. What do you mean by fructose? Fructose. The fruits may contain these kind of sugars, this fructose fruits. Then what is the molecular formula for fructose?
C6H12O6, sir.
Yeah, C6H12O6. Very good. Okay. And what is a functional group present here?
Ketone, sir.
Your ketonic functional group. Very nice. So both glucose and fructose are having same molecular formula, but glucose consists of aldehyde functional group, but here fructose consists of ketonic functional group. Ketonic functional group. And here it will be generally available as D minus fructose. So what about the minus? Minus says it is a levorotatory. Okay, it's not dextrorotatory. Glucose probably levorotatory. Okay, levorotatory. Let's find out the structure of glucose. Here also they found the same rules for whatever we talk about in the case of aldehyde. Almost same similarity will be followed here also, fructose. Okay, so what is that? It may be otherwise called as levose also. So what is the structure of fructose? CH2OH, and here the second carbon only C double bond of group is there. Why? Why? Because it is a ketone. Ketone always present in between the two carbon atoms. That is what we recap. Two carbon atoms. Within this first carbon, third carbon, between them the ketone group is there. That's what the ketone position will be in second position. Okay. So here CHOH remaining all same. That is COH, here H, and here COH, here H, and here CH2OH. Whether it is D form or L form, whether this fructose is in D form or L form.
D.
D. Why? How you said it is D?
OH is on the right. And the
Yeah,
bottom.
from the bottom carbon, bottom to second carbon, the OH group is present in right side. That is what is called D. Then if C5, the OH group on OH group in right side. That's what is called as a D sugar. Okay. What about the D minus? What does the minus says? It's a levorotatory. It is a levorotatory. Okay. Here also it is available in two forms, alpha as well as beta forms. Okay. Here also it is available in alpha as well as beta form. But fructose consists of a five-membered ring. Glucose consists of six-membered ring, but here fructose consists of a five-membered ring only, because most frequent form will be in the form of five-membered ring. Okay. Most frequent form, most available form is in 5-membered ring. Why it form 5-membered ring? So how we can write alpha and beta form? Say for example, CH2OH, I can write it here. Then C double bond O group is here. Then C here H, here OH is here. And then what about that next one? That is a COH, H is here. Then C OH and H is here. Then CH2OH. Yes. Now also the same thing. From that, where it will go and attack for making the big ring, the 5th carbon will go and attack from that, either from this side or from this side also. Okay, that is what can form both alpha and beta form, but it forms only 5-membered ring. Why? Because this is 1, this is 2, this is 3, this is 4, and with the oxygen which is going to form it is 5. Okay, so I'll tell you how. So here also the ketones will also involving in attack with the help of alcoholic group which is present in that 5th carbon, which is also forming a hemiacetal form. So if electron will come and attack, what will happen? This electron will be shifted over. And here it will get negative charge. Here, because of loss of hydrogen, this will get positive charge. That entire group will be attached to this. So here CH2, then C double bond O. Instead of C double bond O, I can write like this. C single bond O. Just a minute. Single bond O, and here C H OH. Here C OH H. The 5th carbon C, and here H. Here CH2OH. Now you can check how many are in ring-like structure. This is 1, 2, 3, 4, and put that as oxygen. That's what as 5-membered ring. It forms 5-membered ring. It can also be involved in attack on the backside also, because that C double bond O group is an sp2 hybridized carbon. It's a planar in structure. It can involve attack in both the sides. Okay, front side or back side can involve attack. So here also it forms, what is that? Here also, sorry, here CH2OH is there. And then CH2OH, here C, and here also CHOH, here COH, here H, here C will be attached here, then here H, here CH2OH. Is that clear? How many carbon atoms totally? And here in this side we have OH group. Am I right? Here in this case, in this side we have, sorry, yeah, OH group. Because this carbon becoming hydrogen, now that hydrogen can be transferred to this now. So here I'll get OH group. And here also the same thing. Here I'll get OH group on right side. Okay, here I'll get OH group on right side. So I can write like this also. So here the CH2 group, instead of writing here, I can write the CH2 group like this for the better understanding. Okay, if the CH2OH group is here, and here instead of writing here also, I can write the CH2OH group here. And here I can write, and the entire thing will be taken over here, and here OH. Is that clear? Now the OH group which is present inside the ring, then what kind of form it is? Alpha or beta?
Alpha.
Alpha. This is called alpha D fructose. Alpha D fructose. We can call it as minus alpha D fructose. Here minus beta D fructose. Is that clear, Kana? It is very, very important. So you have to write the structure like this. So glucose and fructose. So glucose consists of a 6-membered ring, but here fructose consists of 5-membered ring. Here, how to write the 5-membered ring structure? Let's write one by one. So let's write the rules for writing that structure from Fisher projection to Haworth projection. Just a minute. It's hanging. Yeah. So we know that it is a fructose. Fructose, it's a 5-membered ring. 5-membered ring, which means that it is a pentose sugar. Pentose. And here also keep oxygen on top of pentagon, because it forms 5-membered ring means a pentagon. Okay? Pentagon. Then what is that? So also will represent the bonds in what is that? Vertical line. Vertical line. And then we have to give the functional groups. Functional groups. Okay. So just I'm writing one structure, then we can write the another. This is very simple. So here I can write the Fisher projection. The Fisher projection. Sorry. So here CH2OH, CH2OH is here and OH is here. And then here H is here, OH is here. Again here OH is here, H is here. Here also H is here, and here the entire ring will be here, and this O will be attached to that. Then CH2OH. Is that clear? So it's a 5-membered ring. This is 1, 2, 3, 4, and 5. So totally 5-membered. So how to convert this into Howard projection? Here also the same rule will be applied. What is the first rule? 5-membered ring, which consists of oxygen. First of all, I have to draw a pentagon. On the top, I have to provide oxygen. So this is pentagon structure. Okay. It's a pentagon structure. And then how to write that bonds? Bonds will be given in vertical lines. Am I right? Same rule. Write down. Write down. You just memorize this only. So no need to memorize it for left. That will confuse. Write down. That's it. Okay. Or otherwise you can lift up. Lift up or lift up. You can write. So here write down. Right side, what kind of group is there? First carbon. So we can number it. So how we can number it? This is carbon number 1. Is it carbon number 1? No. Actually, this is right side one. Here we have CH2OH. And let's write that, then we can number. Let's write the position, then we can number. So here, right side of that, I have CH2OH. Left side, I have OH group. That's what I have written at top. So first, right side we can write. And second, third carbon, I can write hydrogen here. And fourth carbon, right side, I have OH group. So OH group will be given in bottom. And then fourth carbon, we know that the same hydrogen is there. And here CH2OH is there. Is that clear? And then what about the remaining thing? That this is a OH and this is a H. Okay, right, like we can write this. Then this is a first carbon, this is second carbon, the third carbon, fourth carbon, fifth carbon, and also a sixth carbon. Okay, totally 6 carbons are there, but that can be accommodated in 5-membered ring, that is fructose. Very, very important. Is that clear, Kana? We have to start the numbering from the carbon to the right branch. So where the right branching is there, from that only we have to start the numbering. So this is a carbon number 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay. Is that clear? Is that clear or not?
Yes, sir.
Yeah, here also you can tell me. So how we can write, whether it is alpha form or beta form? It is beta D fructose or alpha D fructose? Alpha beta means you have to check out with the first carbon. OH group is on left side. If it is present in the link side, inside the ring, there is called alpha. So outside the ring, it is called beta. Okay, it is a beta D fructose. Beta D fructose. How I can write the alpha D fructose? What's the difference between that alpha D fructose and beta D fructose? Can anyone say? What's the difference? In the first question, the OH group is on left side. So if it is the OH group present inside the ring, then it is called alpha. Here it is beta. Then we have to write like this. Here OH group will be here and CH2OH will be here. Okay, all remaining all are same. Remaining all and nothing. There is nothing changes here. All are same. OH, H, H, CH2OH. So now, if you look at if you look at what is a change is there. Here CH2OH and CH2OH will be in opposite direction, but here in same direction. Okay, same side. Both are in top, and in beta D fructose, here it is alpha D. In alpha D fructose, both are in top, but in beta D fructose, one is in top, one is in bottom. Is that clear? Is that clear or not, Kana?
Clear, sir.
Okay, we will see remaining in next week. Fine. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Yeah, thank you. Thank you.